Now, one of the areas where people wanted to apply this reaction was in biology or biology-biochemistry related areas. But for this reason, in these cases, when you work with living cells, copper is not ideal, and living cells don't really like too much copper. So for this reason, alternative reactions were sought after. And that brings us to the second concept. Around the same time as the click chemistry concept and these copper-catalyzed click reactions were introduced, Caroline Bertozzi formulated a concept which she called bioorthogonal chemistry. And by this, she meant chemistry that is based on special reactions that can be performed in living systems, in living cells, in living organisms, without affecting or being affected by the myriad of substances and reactions that occur in such very complex systems. As you can imagine, this is definitely not an easy task. So during the 1990s, Caroline Bertozzi had been trying to work out the chemistry and biology of complex carbohydrate structures, complex sugar structures that are called glycans, and they are often located at the surface of cells, as you can see in this picture. Bertozzi and her group had been identifying chemical reactions that could work in living systems, in living cells. For example, they had identified a way to introduce the A-side functionality in living cells and living systems. And they could do so by a type of metabolic engineering approach, where you have a sugar structure, a carbohydrate structure, which is then functionalized with an A-side moiety. And when you grow cells in the presence of this structure, this can be taken up by the cells. It can go through and be processed by the cell machinery and finally become incorporated in the glycans that you find at the cell surface, as you can see here. Now, once this fantastic copper-catalyzed click reaction had been discovered, shortly after, Bertozzi could also identify a metal-free alternative. And you can see the alternative here. And this alternative was based on a so-called strained alkyne, as you can see. This is an 8-membered octagonal alkyne, where the alkyne's moiety is actually twisted in the sense that it becomes much more reactive. And this alkyne structure, you can then, of course, functionalize any way you want. In this case, for example, with a molecule that can emit green light. And if you then add this strained alkyne to the cells where you have this A-side functionality, these two components can click together very efficiently, and now you have labeled the glycans at the surface of the cell, and you can study where they are under the microscope. And that's exactly what you can see on the next slide here. Here you see a number of cells, and the blue part here is the cell nuclei that have been labeled blue. And you can see the green, shining green surface of the cells where you actually have those glycan structures. So these two